Welcome to the Deep Dive. We're here to get straight to the core insights from important research. Today we're looking at something pretty fascinating in the world of AI specifically, how large language models, LLMs, are getting better at complex reasoning. They're making incredible progress, but there's this interesting challenge that pops up as they improve. So our deep dive today is centered on a recent research paper. It's titled Beyond Pass at 1, Self-Play with Variational Problem Synthesis Sustains RLVR. Sounds a bit technical, maybe.
A little, yeah.
But it really focuses on a key issue with a common training method called reinforcement learning with verifiable rewards, or RLVR. Let me just quickly set the stage for you on some terms here. Pass at 1, that just means the model nails the answer on its very first try.
Right.
But pass at K, that's different. It means the model finds at least one correct answer within, say, K attempts, maybe 32 attempts. So pass at K really tells you more about the model's range, its ability to find different paths to a solution, not just its first guess.
That's a good way to put it. It's about the breadth of problem solving.
Okay, so RLVR. It's been great for boosting that initial success, that pass at 1, but there seems to be a catch. It can sometimes reduce the variety of solutions the model comes up with, and that limits its ability to find those more complex answers, which hurts the pass at K score and, well, ultimately stops it from getting continuously better.
Yeah, what's really interesting and maybe a bit counterintuitive is why this happens. When these LLMs are trained over and over on the same set of problems, they can almost start to, well, memorize the right way to get the reward.
Learning?
Sort of, yeah.
Yeah.
Reduces their drive to explore different ways of thinking, different solutions. The paper calls this entropy collapse. You can actually measure this. It's called training entropy, basically.
Yeah.
How much variety is there in the model's attempt. And with standard RLVR, that variety, that entropy, tends to drop over time. So the model gets really good at the known stuff, but its ability to innovate or tackle harder variations, that kind of stalls out. Think of it maybe like practicing only scales on a piano. You get very precise, but you might struggle to compose something new and complex.
Right, that makes sense. So that's why this deep dive matters for you listening in. We're going to unpack this new strategy the paper introduces. It's called self-play with variational problem synthesis, or SVS.
Yes.
Our goal here is to give you a clear picture of how SVS tackles this whole entropy collapse problem. It seems to offer a new way for LLMs to keep learning and improving their reasoning skills more sustainably. So it feels like a bit of a trade-off then. RLVR gives you that initial boost, that quick win on pass at 1, but maybe at the cost of long-term broader reasoning ability. Could you unpack that initial success first, and then maybe why it becomes this double-edged sword?
Absolutely. RLVR is initially very effective because it efficiently steers the model towards solutions that are known to be correct, the ones that get the reward. It's good guidance. But the entropy collapse happens as the model becomes too focused on those known reward paths. Its output diversity shrinks significantly. Now, that can make it faster and better at hitting the target for pass at 1?
Yeah.
Sure.
More efficient.
Exactly. More efficient for that first shot. But it limits its capacity to explore other potential reasoning paths, maybe more complex ones. So it struggles to improve its pass at K score, which, like you said, is arguably a better measure of its underlying reasoning power. The research clearly shows this policy entropy metric just steadily goes down during standard RLVR training.
So the practical result is it hits a ceiling. The model kind of stops being curious, stops exploring new ways to solve things. It's not just about getting good, it's about staying adaptable, right?
That's a great way to think about it.
And the paper points out that trying to fix this by just finding more and more diverse human-created problems is really hard. It's expensive, time-consuming, and you need problems where you can actually verify the answers reliably.
Right. They show that even if you augment the training data, you might slow down the entropy decline a bit, but you don't really solve the core issue of the model losing its exploratory drive over the long run. It's a Band-Aid, not a cure.
Okay, so if standard RLVR runs into this entropy problem and getting enough new, diverse data is a major hurdle, where do we go? Does the model need to start teaching itself somehow? This seems to be where SVS comes in. It sounds really clever, this idea of an online self-play mechanism where the model makes its own problem.
You nailed it. That's the elegance of SVS. It's designed as this continuous, self-contained improvement loop. It's online, meaning it happens dynamically during training. So the paper lays out the workflow, right? First, the LLM tackles problems from its starting training set. They call this original problem solving. Nothing new there.
Standard stuff.
Standard stuff. But then comes the clever part, identifying challenging problems. SVS is smart about this. It doesn't just pick any problem to riff on. It focuses specifically on problems where the LLM is, let's say, moderately successful, not acing them, but not failing completely either. Maybe getting them right between like 12.5% and 50% of the time.
The sweet spot for learning.
Exactly. That's where the real learning potential is.
Wow.
Then, using its own correct solutions to these challenging problems as a starting point, the model does something called variational problem synthesis.
Okay.
It generates new problems. But crucially, these new problems have to keep the same original correct answer, but present the problem differently. Different structure, different wording, different context. This avoids needing new human labels, which is a huge bottleneck, and tackles that data scarcity problem head on.
I see.
Then the model tries to solve these new problems it just created. That's synthetic problem solving, and the whole thing loops. The model learns to solve and learns to synthesize good problems, feeding its own growth.
That loop sounds powerful. But isn't there a risk? Couldn't the model just learn to generate slightly reworded versions of problems it already finds easy? Or maybe problems that accidentally give away the answer? How do you ensure these self-generated problems are genuinely useful and push the model? What's the secret sauce there?
Right, that's the critical question. If the generated problems are too easy or somehow flawed, the whole loop falls apart. The paper solution is really smart. Reward shaping for problem synthesis.
Reward shaping.
Yeah, so instead of just rewarding the model for creating any problem it can then solve correctly, SVS gets specific. It gives positive rewards only when the model synthesizes a problem that turns out to be of moderate difficulty for the model itself.
So it's rewarded for creating problems that are in that same sweet spot you mentioned earlier.
Precisely. The reward system encourages it to generate problems where its own solve rate falls within a specific range, say 12.5% to 62.5% accuracy. This discourages it from making problems too simple or accidentally embedding hints. It pushes the model to create genuinely challenging variations that force it to strengthen its reasoning, not just practice what it already knows. The paper even has examples showing good versus bad synthesis based on this reward structure.
Okay, that makes a lot of sense. You're incentivizing the creation of genuinely challenging practice. So if this SVS system lets an LLM become its own quite rigorous tutor, always pushing itself with problems right at its learning edge, what does that actually achieve? What are the measurable results? How does it make the model better?
The results reported are pretty significant, actually, across several areas. First, let's talk about that policy entropy, the measure of solution diversity we discussed.
Right, the thing that usually collapses.
Exactly. Well, the data shows SVS maintains that policy entropy stably throughout the training process. It doesn't drop off like it does with standard RLVR. This stability is key because it means the model keeps exploring, keeps trying different approaches, and doesn't just settle into a rut. It stays curious, as you put it earlier.
So it stops the plateauing.
It seems to, yeah. And second, this translates directly into better pass-at-K performance, especially on hard problems. The paper highlights really impressive gains like absolute improvements of 18.3% and 22.8% in pass-it at 32 scores on tough competition-level math benchmarks, AIME24 and AIME25.
Wow, that's substantial.
It is, especially because standard RLVR showed almost no improvement there. It suggests SVS isn't just optimizing that first guess. It's genuinely improving the model's ability to find a correct solution, even when it takes multiple tries developing those Plan B and Plan C options. And third, it's not just about improving pass-at-K for a few attempts. SVS seems to push the whole reasoning boundary outward. The graphs show that while standard RLVR might only boost pass-at-K for small K values, SVS gives significant lifts across all K values they tested, up to 124 attempts. This means it's enhancing the model's exploration capability across a much wider range, especially on challenging benchmarks like AIME25.
So it's a deeper, broader improvement in reasoning.
That's what the evidence suggests. Plus, it seems quite robust. They tested it on different model sizes, from 3 billion up to 32 billion parameters, and across 12 different reasoning benchmarks. They saw consistent improvements, averaging around a 3% absolute gain over the baseline method. It doesn't look like a one-off trick for a specific setup.
And does it only help with math problems, or does it generalize?
That's another really interesting finding, actually. You might expect that focusing so much on synthesizing and solving math problems could make the model worse at other things overfitting, right?
Yeah, makes sense.
But Table 3 in the paper shows the opposite. SVS didn't just avoid hurting performance on general QA and coding tasks like MMLU Pro or HelloSwag. It actually improved it slightly. This suggests the self-play mechanism might be enhancing the model's general instruction following and reasoning skills, not just its math prowess. It helps it become a better learner overall, perhaps.
That's quite remarkable. So wrapping this up, this deep dive really highlights SVS as a powerful new way for LLMs to teach themselves. By continuously creating diverse, challenging problems, they maintain that crucial exploratory drive, push their reasoning limits further, and get better not just at one thing, but seemingly across the board.
It's a very promising direction. Definitely a self-improving loop.
It really makes you wonder, doesn't it? Thinking about this for you, our listener, what new frontiers of reasoning could we unlock when an AI becomes its own best, most challenging teacher? When it learns not just to find answers, but to master the art of asking the right hard questions of itself. Something to think about.